Welcome back, everyone. So we are done with regression. We had our 4 lectures on regression, and that's that. We're going to go back to classifiers today. And today we're going to be talking about a very different style of classifier called decision trees. Before we start, let me just note that the midterm will cover everything up, well, the midterm is a week and a half from now. It will cover everything up to and including the last lecture, Monday's lecture. So to the end of regression, the 3 lectures that we'll have before, the last 3 lectures before the midterm aren't going to be on the midterm. They'll be covered on the finals, starting with this material today. A decision tree is a nonlinear method for classification, and it can also be used for regression, but it's usually used for classification. And by nonlinear, I mean it does not give a linear decision boundary in general. So a decision tree is a standard computer science style tree with 2 types of nodes. As in most trees, the internal nodes serve one purpose, and the leaf nodes will serve a different purpose. And what the internal nodes do is they test points feature values. But at each node in the tree, we usually test just one feature. So in an internal node, you've got a test point. We look at one feature of that test point. And based on that, we branch either down to the left child or down to the right child. There are exceptions to this, usually just one rule, but 99% of the decision trees you'll run into are just testing one feature at each internal node of the tree. And then when you reach a leaf node, when you get down to a leaf node, you can't go down any further. The leaf node specifies a class or a regression value and tells you, okay, this point, I predict that it is in this class. For instance, let's look at a decision tree for, I want to look at the weather today and picnic in the park. And so I'm going to have a decision tree. Assume that we have 3 different features. And so one of those features is what we call the outlook, which is the prediction of whether it's going to be sunny, overcast, and if it's sunny, we're going to hit a second internal where we're going to look at the humidity. So the idea is if it's a sunny day, if the humidity is really high, I don't want to go to the park and have a picnic. But if the humidity is reasonable, I'll go have my picnic. And so we have 2 cases here. If the humidity is over 75%, I say, no, I'm not going to have a picnic. But if it's less than or equal to 75%, that's good enough, dry enough that I'll go have my picnic. Now, if it's overcast, in that case, I have no objections. I'm just going to go on the picnic because the weather will be comfortable, not too cold. If it's raining, Then maybe I'll look at a third variable. I'll ask, how strong is the wind today? Because, you know, there's a nice gazebo in the park. You can have a good picnic in the gazebo, enjoy the fresh air even if it's raining, unless you have a high wind blowing rain into the gazebo, in which case I don't want to go. So if the wind speed is greater than 20, I say, no, it's going to be wet in the gazebo. If it's less than or equal to 20, let's go on a picnic. So that's the idea of a decision tree. And in particular, you'll notice that not all the variables, not all the features are of the same type. We have two quantitative features, humidity and wind, but outlook is not a quantitative feature. It's just a three-way choice. And one thing decision trees are very good at is mixing different types of features, quantitative features with binary features or multi-way features that are discrete. That is one view of a decision tree, but there's a second view you could make where you actually draw the feature space and subdivide it into pieces. So let's check that out. What I'm drawing here is a box where the horizontal axis is the x1 axis, and the vertical axis is the x2 axis. Now, there are actually three features. I don't feel like trying to draw a three-dimensional box right now, so you'll just have to assume that we're stacking towards you out of the screen for the wind direction. X1, the first feature, is not a quantitative feature again. It's just a three-way choice between sunny, overcast, and rain. And so I can just draw my feature space by dividing it into three chunks that way. If we're sunny, well, remember, next we're going to look at the humidity and make a decision based on that. So let's mark the humidity scale. Here's 25%, 50%, 75%, 100%, 0 at the bottom. And our decision tree is checking whether the humidity is greater than 75%. And if it is, nope, no picnic. If it's not, yes, picnic. In the overcast box, yes, picnic. In the rain box, well, that's where you need the third dimension. So if you can imagine, this is really a 3D rectangular prism, and I'm going to take this box here, and I'm going to divide it by slicing it the other way. So I will simply express that by saying you need to check x3 and make a decision based on that value. But the point is we have a three-dimensional feature space, and it's actually getting cut up into rectangular prisms by the decision tree. And so that's one of the, characteristics. Again, I said there are exceptions where you look at more than one feature at a time in a decision tree node, but 99% of decision trees, you just do this. I repeat, it works well with different types of features, even when you're mixing different types of features. So in this case, we have a categorical feature, which is sunny, overcast, rain, and we have a couple of quantitative features. And obviously, they mix very nicely, which you cannot say that about support vector machines or discriminant analysis. Another thing that makes decision trees really famous and popular in certain applications is that they're really good result. So a reminder that decision trees are sometimes used not just so a computer can classify things, but so that we can get some wisdom about what are the important features, what are not the important features, that we can convey to other people, or that we can build a science on top of. And so being able to infer principles from what we've learned in our decision tree, well, decision trees are obviously really nice for giving you simple explanations. Lastly, the decision boundary can be as complicated. So in this respect, it's almost the opposite of a linear classifier. If you make the tree deep enough, you can get as much fine distinction between different classes as you want. Let me show you a picture that puts some of these into relief. In this figure here, which is my redrawing of a figure from your textbook, there's two different data sets here. So I'm showing one data set on the left, and that data set just naturally works well with a linear classifier. It's actually linearly separable, so a linear classifier can perfectly distinguish the red points from the blue points. But the linear separability is not a horizontal or vertical line. And if you use a decision tree, since we are more or less forced to only use horizontal and vertical lines, you have to refine the decision tree a lot more to be able to distinguish all the blue training points from the red training points. So this is an example of a data set where linear classifiers have an obvious advantage over the decision tree in terms of complexity and probably generalization too, because the data is actually really well fit for a linear classifier. But on the right, we have the opposite situation. So here is a data set where a decision tree very naturally models what happens in the data. Because what happens in the data here is this corner is blue, everything else is red. There are a surprising number of real-world data sets where things break down kind of like that. And in this example, a linear classifier, obviously can't get 100% training error. Those points are not linearly separable. So which classifier is better really depends on the character of the data. Questions? Absolutely. So the question is it possible to combine the two? And in fact, you don't have to use an axis-aligned decision boundary within each node of the tree. At every node of the tree, you could actually run some other classification algorithm, like an SVM or even a neural network, and use that to subdivide the cell. But when you do that, you lose one very big advantage, which is speed. One reason why decision trees are very fast, only one feature at each node. If you have to look at all the features at every node of the tree to decide which way you're going to branch, you're slowing yourself down a lot. Other questions? By the way, I'll talk about that a little bit at the beginning of next lecture, too, on Monday. Yeah. You could, if your data fits that, if you have lots of diagonal lines through your data, but they're all kind of in the same orientation, then yeah, you might run some pre-process that tries to figure out what the right orientation is. Sure. One thing about decision trees is they're infinitely flexible. Anything your imagination can decide to do with them might work. There's so many, many different ways to modify a decision tree for a particular application that I couldn't possibly talk about them all. Talk about a few of them next lecture. All right, let's get down into the weeds of how you build decision trees. And we will consider classification first. Assume we're using a decision tree as a classifier. I will talk about regression briefly on Monday, but not today. To build a decision tree, we use a greedy algorithm, which builds the tree from the root on down. So it's a top-down learning algorithm. And although you could formulate it as an optimization problem, it would be an NP-hard optimization problem. So generally we use heuristics to try to find nice splits, but not necessarily the optimal split in practice. So let me first sketch out the high-level algorithm for building a decision tree, with some of the details left out. And I want to say the algorithm is kind of obvious. Like if you sat down and thought about it, this is probably what you would come up with. It's been rediscovered many times. It is a naturally recursive algorithm. This is just a task that really fits recursion well. So the idea is, let's suppose that we are processing one rectangular prism in the tree. And let's suppose that we have decided that some subset of the training points are going to be in that box. So what I'm going to do is I'm going to have a set called S. S is the indices of all of the training in this particular box that I'm about to process. Like, for instance, it might be this box right here, and I'm going to process it and then decide where to split it. And so S tells us the indices of these blue points inside the box. When you start building the decision tree, you're going to start at the root node, and the root node is going to represent a box that encloses all of the training points. The first time you call this recursive procedure that I'm about to show you, you will give it a set with all of the numbers from 1 to n. But then, as it recursively calls itself, it will call itself on smaller and smaller subsets of the training point. So here's the recursive algorithm. I will call it grow tree. The input is just a set of indices, or you can think of it as a set of sample points that fit in one particular box. And the first check whether all of those training points in that box have the same label. All right, so if for all the points in set S, the label is class C, always for the same class C, or put it another way, if all of these points have the same class, with no exception, then we build a root node. Or sorry, because I can label all the points in that box with one class. They're all the same class. And when we have a leaf node that contains only one class, we say that that leaf is pure. So decision tree where all the leaves are pure. You don't have to do that. That's one of the many things you can change if you want to. But for now, all the leaves. All right, so else, not all the points in the box are in the same class. So what we want to do is we want to try to split them up into the different classes. And to do that, we need to choose a split. Specifically, we need to choose which feature we're going to split on, index j. And if j is binary, then we'll have a true child and a false child. But if j is quantitative, then we also have to choose a splitting value, which I'll call beta. All right, so this is the hardest part of the algorithm. And we're going to spend most of the rest of this lecture talking about that line of code. So I'm going to put a little asterisk here and come back to this later. Let me finish the algorithm first, and then we can come back and discuss how on earth do you implement that line of code. Once I've chosen a split, though, things are very straightforward. What I do is, you can think of it as, let's pick all the points that are to the left of the split, and let's pick all the points that are to the right of the split. Or maybe it's above the split and below the split, whatever. But the left child of the node I am currently building is going to be devoted to all of the points in the big box for which that feature is less than beta, and the right child will be all the remaining points, the ones for which the same feature is greater than or equal to beta. I decided that when you have equality, when you have a training point for which that feature is exactly beta, we'll put it in the right child. And that's a totally arbitrary decision. I could have put them all in the left child. Just be consistent. You know, put all the betas in the same child. All right, so having done this, now I am going to recursively build a decision tree for the first set, recursively build a decision tree for the second set, and then make those become the left, well, the subtrees rooted at the left and right child of the current node that I'm building right now. So here's what that looks like. Here's the slightly tricky recursive part. We're going to create a new node. And in that node, we will store the splitting information. You know, we're splitting on feature j. The splitting value is beta. And the other two things we need to store in a tree node are the left child and the right child. We'll build those recursively right now. So here's a recursive call that builds the left subtree. Here's a recursive call that builds the right subtree. Except for explaining how we do the asterisk part. Are there any questions about this? All right, so let's get back to the asterisk. How do we choose the best split? All right, well, the standard algorithm is you try all of the splits. Meaning, for every feature, you try splitting on that feature. And within one feature, for every splitting value that might give you a different outcome, you try that splitting value. A lot of different things to try. That's okay. So when we try all the splits, what we're going to do is we're going to assign a score to each possible split that we try. And we're going to pick the one with the best score. So that's going to involve a cost function. And so given a set S of inputs, you can think of it as a set of training points. We're going to a cost for that subset of the training points. And so when we're considering different splits, we're going to score the two children of each split. So for this split, I construct the left child, I construct the right child, I score the cost of each of those two children, and I look for the split that gives me the two costs that I like best. That means you have to combine the cost of the left child and the right child. So there's several ways you could do that. The simplest way is you can choose the split that just minimizes the cost of the left child plus the cost of the right child. And sometimes you might want to do that, but it's not really what I recommend. Reason being that sometimes you have a very uneven split. Like maybe the left child gets 90% of the points from the parent and the right child only gets 10%. In that case, I would say that the cost of the left child is more important than the cost of the right child. So if you agree with me, then it makes sense to do a weighted average rather than just the average. So we weight each child according to the number of training points that get allocated to that child. And so that's gonna look like this. Here's the cardinality of SL, the training points assigned to the left child, times the cost of SL, plus the cardinality of SR times the cost of SR. And since this is a weighted average, we divide by SL plus SR, which, incidentally, this is always equal to just the cardinality of the parent node. So that doesn't change. That's going to be the same for every split. You can kind of ignore that denominator and just compute the numerator. And again, here I'm using vertical bars to denote set cardinality, meaning the number of points in a set. So that's the basic idea of how we score each different. But now we need to choose a cost function. And this is a black art. I can't give you a mathematically rigorous reason why such and such is the best cost function. But since this is a heuristic, we can do a little bit of reasoning about it. Now, the way I'm going to formulate my heuristic is I'm going to start by giving you a not very good heuristic. I want to start with the simplest thing we could think of and show why it's flawed, and that will motivate a more sophisticated approach. So here's our first use a cost function. And again, just to be clear, this is a bad cost function. I'm not recommending it. All right, so first of all, we ask, what is the majority class? Or if there's more than two classes, what is the plurality class? What is the class that has the most points in the node? And then we just set the cost function to be the number of points that are not in the plurality class. So in other words, if I were to label this node with a class and make it a leaf node, how many of those training points would I get wrong? All right. To show you why this is a little bit flawed, I want to give you an example. Splits. Suppose that the parent node has training points from 2 different classes, and 20 of them are in class C, and 10 of them are in class D. And suppose I ask, what happens if I split on feature x1? Well, in that case, it turns out we'll get 10 of class and 10. And the right child will get the other 10 of class C and none of class D. Let's compare that with a second possible split of the same node. So again, same parent node, but this time we split on some other feature x2, and this split gives us one child with 10 of class C and 5 of class D, another child that's the same, 10 of class C and 5 of class D. All right, so the parent node has 10. So the majority is class C, but there are 10 in class D, so that's the cost. Look at the children of the left split. The cost of this left child is 10. The cost of this right child is 0. The cost of this left child is 5. And the cost of this right child is 5. So suppose that our algorithm is just to use the sum of the costs of the 2 children. Well, you'll notice that the cost of the left child and the cost of the right child is 10 for both splits. And there are many other possible splits you could do as well that would have the same cost. So this is a problem that it doesn't really distinguish between a wide variety of different splits. I would argue that this is the better split. Why do I think this is the better split? Because it gives you one node that's pure. A pure node's a good thing. You can make it a leaf node. You can stop there. Then you just have to keep splitting up the left child. The other side is, in a way, the worst split you could possibly get. Exactly half of class D goes to the left, exactly half goes to the right, exactly half of class D goes to the left, exactly half goes to the right. You really haven't made much progress in separating the C's from the D's at all. I mean, eventually, if we keep splitting, you'll get down to 1 point in each leaf node, and you'll succeed. So I can't say that we've made no progress, but I'll say we have made disappointing progress. So I think a good cost function should choose the one on the left. We've seen that if we just take the sum of the left cost and the right cost, it doesn't choose. But what if we take the weighted average? Well, if we take the weighted average of these costs, it actually chooses the one on the right. It chooses the bad one. So I don't like this cost function. I want a function that better distinguishes what's good and bad about these 2 splits. Any questions about that before I go on? So that's the end of the bad idea. Let's try a different idea. And this one I claim works well and is used a lot in practice. So instead of measuring the size of the minority, we're going to measure something else called the entropy, which is an idea from information theory. We're trying to measure how much information is encoded in each split. Maximize that is one way to think about it. So what is entropy? a random class variable, by which I mean this variable might be class C, it might be class D. You roll the dice and you get some class. And let's suppose that when you draw that random variable, when you select a variable from that distribution, the probability that you get class C is P subscript C. And the probability you get class D is P subscript D, and so on. So one quantity associated with this random variable is the surprise of the outcome. So suppose you draw this random variable y, and you find, oh, I got class C. Am I surprised? The surprise of y turning out to be class C is minus base 2 logarithm of that probability, PC. So don't let that minus sign make you think that this is a negative number. It's always non-negative. It's just that since PC is always less than or equal to 1, this logarithm itself will be negative, so we have to undo that negative sign. So why does it make sense to call this thing the surprise? Well, let me give you two examples, the two extreme examples. Suppose that we are looking at an event with a probability of 1. In other words, there's a 100% chance that my random variable will be C. Then when I look at my random variable and I say, oh, it's C, I'm not surprised at all. So getting the expected result gives us 0 surprise, because I already knew 100% chance it's going to be C. At the other extreme, suppose that this random variable is never class C. It's always some other class. So now getting class C is an event with probability 0. Well, that gives us infinite surprise. When you take minus log of 0, you get infinity. Which makes sense again. If something that absolutely cannot happen happens, you should be infinitely surprised. And then there's a sort of a scale in between from 0 surprise for events with probability 1, moving up to infinite surprise for events with probability 0. So in information theory, the surprise is equal to the expected number of bits of information that you would need to transmit to somebody else to let them know what you observed, assuming that that recipient already knows the probability of those different events. One thing that's weird about this is that since we're taking the log of probability, often we don't get an integer, often we get a fraction. Like you might say, what does it mean to send somebody 7.3 bits? Well, you can't send somebody 7.3 bits, but if you have many, many different random variables rather than just one, then you can agglomerate the information about their values into a single message that does use fractional bits to encode the data. So if you want to know more about that, take an information theory course. But in short, this is how many bits of information it takes to convey what happened, what event happened, to someone who knows the probabilities of those events. All right, so that leads us to the entropy of an index set. And we're going to define that to be the average surprise. Okay, but what is the surprise of an index set? Well, what we're going to do is we're going to sum over every possible class that might happen. the value of PC log 2 of PC. So average surprise, because you get class C with this probability, and so when you take the mean, this gives the mean of all the surprises for all the different classes. But wait, what is this probability here when we're talking about an index set, you might ask? Well, here's the definition of PC in this context. We count how many of our indices are in class C. We divide by the total number of training points in that rectangle. So that's the proportion of points in S that are in class C. So the way to think about it is, you've got a bunch of training points in a box. We take all those training points and we throw them into a hat. Then we reach in and stir and pull out one training point, and PC is the probability that that training point will be in class C. That's all it is. Maybe just to be even more explicit, here's the hat. This hat has 3 red points and 5 blue points. So the entropy of this hat is minus 3/8 of log 3/8 minus 5/8 of log 5/8. Always logs for information theory. So let's sanity check this with a few examples. Suppose that all of the points in our set belong to the same class. In that case, the entropy of our index set is minus 1 times log of 1. And log of 1 is 0. So the average entropy is 0 if all the points are in the same class. Okay, what if half of the points are in one class and half the points are some different class? Well, in that case, you need to sum over each class. There's 2 classes. For the red class, we get minus 0.5 log of 0.5. For the blue class, we also get minus 0.5 log of 0.5. And so that's an entropy of 1. But we can go even higher than that. The third example we'll consider is, suppose that there are n points in my hat, or n points in my rectangular prism, and suppose they're all different classes, so n different classes. Well, in that case, the entropy is minus the log of 1 over n, which is the same as the log of n, base 2 log of n. So as the points get more and more different from each other, the entropy goes up. Now, the entropy is the expected number of bits of information that you would need to identify the class of a sample point S chosen uniformly at random. So it makes sense, for instance, that if you know that half the points are in class C and half are in class D, and you want to transmit the color of one of those randomly drawn points to somebody else who knows the probabilities, that takes 1 bit. It makes sense that if the recipient knows that all the points are in the same class, you only have to send 0 bits, because the recipient already knows the answer. And if you have n different choices, it makes sense that you need log 2 of n to tell somebody which choice got made. Is there a question? Yeah. Oh, yeah, thank you. Sorry, so there is a missing minus sign here. Uh, if you repeated my error, please add a minus sign there. Thank you. All right, so what I want to do now is let's consider the case where there's two classes, but they're not necessarily a 50-50 split. Then what does the entropy look like? Well, I will show you a graph of that. So in this graph here, the horizontal axis is PC, the probability that a randomly drawn point is in class C. Or to put it another way, what proportion of the points in the hat are in class C? And again, this graph is just for the case where you only have two classes. So we know the probability of the other class as well is 1 minus PC. So we only need a one-dimensional axis to plot the entropy, which is the vertical axis here. And, well, it's a nice concave curve that's 0 at the ends, because at the ends you know what class you're going to get, and maximized in the middle. It's maximized when exactly half the points in the hat are red and half the points in the hat are blue. All right, so let's use this. Let's use this entropy. And the way we're going to score our splits is we're going to take the weighted average of the entropies in the left child and the right child, and we're going to use that in our decision tree. So again, the score for each split is the weighted average entropy between the left child and the right child after you do the split. And I will write that as H subscript after is, again, the cardinality of the left child times the entropy of the left child plus the cardinality of the right child times the entropy of the right child divided by the total number of training points in the children together, which equals the total number of training points in the So we're going to look at all these different splits, and we're going to choose the one that minimizes this. But minimizing this is also equivalent to maximizing something called the information gain. So the information gain is the entropy of the parent minus the entropy, weighted average entropy of the children. Now, again, maximizing this is exactly the same as minimizing this. I don't really get anything new by throwing HS in here. But the reason it's nice to think about HS is this. As you go down the tree, the information gain is never negative. It could be 0, but typically it's positive. And so this is actually a measure of how much additional information you have about your points with each split as you walk down the tree. Let me give you an example where we'll actually just quickly work out these numbers, coming back to this example here where we have this parent node again. And Let's suppose I do a split with the property that I wind up with 10 copies of Class C, 10 Class C training points and 9 Class D training points in the left, leaving behind 10 Class C points and 1 Class D point for the right child. All right, so the entropy of the parent is minus 20/30ths, log of 20/30ths. By the way, LG is a shorthand for a base 2 logarithm. Minus 10/30ths of base 2 log of 10/30ths. And that is approximately equal to 0.918. Now let's do the same thing for the children. The left child its entropy is minus 10/19ths log 10/19ths minus 9/19ths log of 9/19ths, and that is approximately 0.998. So it actually has worse entropy than its parent. Fortunately, the other child node, the right child, is going to have a much better entropy than its parent. Having dropped down to 0.439. And now if I take the weighted average, then that is H subscript after. And remember, we're applying this formula up here. So when you plug that into your calculator, you get 0.793. And it's good to see that this is smaller than the parent's entropy. And the information gain is the difference between those two numbers. So in this case, the info gain is 0.125. Any questions about that? All right, so one thing is interesting to know about the info gain. The information gain is always positive with two exceptions. And in those two exceptions, it is 0. It's never negative, but it can be 0. And there's two circumstances where that happens. The first one is when one child is empty. And I hope that is not surprising if you have a parent node with these sample points, and all of those sample points go into the left child, leaving the right child empty, then we have made no progress, obviously. This is a useless split. This is a bad split. This is a dumb split. We never want to do this. But that's one of the two situations in which the information gain. The second example, which can come up, is the case where the proportions of the red and blue points don't change. They're the same in each child as they were in the parent. So for every class, the number of points of that class the probability that a point has that class in the left child is equal to the probability it has that class in the right child. That case there, that already came up in one of our examples. Remember, we had this split here where the parent has a 2-to-1 ratio of class C to class D. So do both children. So that's also 0 information gain. So that's the only two circumstances where the information gain is not positive. So I want to try to convey a little bit of information about why it works this way. So recall the graph of the entropy. So we had a variable PC varying from probability 0 to probability 1. And it kind of curves up like this, reaching a maximum of 1 at about 0.5. And imagine that we represent the left child. It turns out that its probability puts it here, and the right child, it turns out that its probability puts it here. So what are the possible values for the weighted averages of those two entropies? Well, weighted averages all fall on this line. Like, for instance, the exact average would be exactly halfway between them, but if you choose the weights accordingly, the weighted average could be anywhere on that blue line. And so whatever the weights are, you wind up with some point whose vertical distance is h after. Well, the proportions we use in the weighted average also determine the entropy of the parent, in that if I draw a vertical line up from h after, then this gets me to the entropy of the parent. Information gain is actually the length of this vertical line. And if I use the entropy, or for that matter, any other function that's strictly concave, like everywhere it's a frown, everywhere it has negative curvature, then the information gain will be positive in that case. On the other hand, we can consider a flawed metric for the sake of comparison. So let's consider another cost function where the cost of probability PC is the percent misclassified rather than the entropy. And so in that case, it maxes out at 50% misclassified if there's only two classes. And it looks like this. This is what the cost function looks like as a function of PC. So you'll notice that this function is concave, much like the one on the left, but it's not strictly concave. There are places where it's flat. And so if you try to repeat the same idea here, you take the cost of the left child there, then once again, the weighted average of those two costs lies somewhere on this line, but you don't get any gain. No matter where your weighted average is, you don't get an improvement in the weighted average of JS. They're all the same as the cost of the parent. Now, this doesn't always happen. You could, for instance, have, if the left child was here, then your line would be strictly below the function and you would get a better result. But when both percentages are greater than or equal to 50%, it just can't distinguish between different splits. Any questions about that? Yeah. Why is the line vertical here is the question. And value of h after, this thing here, is based on weighted average of the 2-point sets. But PC itself, the PC of the parent, like the parent set S, is also a weighted average of the PC of the left subset and the PC of the right subset. So that means that the PC of the parent is going to be right here. And so that means that this is going to be the entropy of the parent. Other questions? Yeah. I mean, if you slide here? No, like just close to each of us. Seems like the entropy would be higher if well, if you move one, you have to move the other. So the point here is that the blue line is everywhere below, or the blue line segment is everywhere below the black curve, except at the endpoints, of course. So yeah, you always have to compare two numbers that have the same x coordinate, and the info gain is the vertical. By the way, the entropy is not the only function that works well. You know, even though it makes sense in information theoretical terms, it's kind of, anything with this curve tends to work well in practice. So if you don't want to compute logarithms, you can actually just use the polynomial p times 1 minus p, and it works almost as well as the entropy. But it's cheaper to compute. To say about cost functions, but I want to go back now to say some more things about choosing a split. So might have binary features that are always only two possible values, or you might have quantitative features that have continuous values, or you might have something with 3 or more discrete values. So each of those is treated a little bit differently. If you have a binary, then obviously there's only one way to split a binary feature. You have a child for true and you have a child for false. Or to put it another way, you have a child for xi equals 0 and you have a child for xi equals 1, or whatever values you've chosen for your binary. But sometimes you have a discrete feature that has more than 2 possible values. Like rainy, overcast, sunny. For that, there's several things you could do, but what is the right thing to do almost certainly requires knowledge of application. Sometimes it makes sense to use multi-way splits like we did at the beginning of the lecture, where we split 3 ways on sunny, overcast, rain. Sometimes it makes sense to just use 2-way splits and use several levels of the tree to work out all the different discrete features. That makes the most sense if you can group certain features together that are similar. But for continuous valued variables, I'll call them quantitative variables, you need to do something a little more sophisticated. So here's how we're going to make this fast. We are going to sort, like when we're processing a particular node in the tree, we're going to sort the values of that feature for all the training points in the index set. And then we're going to try splitting between each pair of unequal consecutive values. By the way, when I say sort, I suggest a linear time sort if n is really big. Radix sort it. Radix sort works very well. And so think of this as something that can and should be done in linear time. But after we're sorting, we need to compute a bunch of different entropies. We've got, if we're sorting n points, now we have n minus 1 different possible splits. We need to compute an entropy for each one of those splits. How do we do that fast? Here is the clever trick that allows you to do that in linear time instead of doing it in quadratic time. As you scan through this list, sorted from left to right, you just need to observe that you can update the entropy in order 1 time per split. You don't have to spend order n time computing the entropy. So this is really important for getting a fast algorithm. And so here's the rough idea. Suppose that I just have one-dimensional, well, this is my feature. I'm drawing a one-dimensional data because I only care about one feature at this moment. And I have, let's say, number line, and along this number line, here are a couple of points in class C. Here are 3 points not in class C. So if those are the values, there's only 4 ways that I can split this data. These 5 points can be split here, 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 or here. So I need to compute the entropy for each of those 4 splits. How do I do that? Well, for each one of those splits, I need a count. I need to count for instance, for this split, I need to count how many C's are to the left of that split. There's 0. How many X's are to the left of that split? There's 1. How many C's are to the right of that split? There's 2. How many X's are to the right of that split? There's 2. If I have those 4 numbers, I can compute the entropy. But I need to do that for every split. So here it's going to be 1C, 1C. Here it's going to be 1C, 1C. Here it's going to be 1C, 1C. Here it's going to be 1x, 2x. Here it's going to be 2x, 1x. Here it's going to be 3x, 0x. All right. So as I'm going from left to right, the first one, for the first split, it's going to take me linear time to compute those 4 numbers because I have to look at all of the points to do it. But then I can update them to the next 4 numbers in constant time. All I have to do is look and say, oh, there's a C here, so I increase this by 1 and I decrease this by 1, relative to the one on the left. That's all I got. In constant time, I can compute this. In constant time, I can compute this. In constant time, I can compute this. The first one took order n time, but that's okay because all of them together take order n time. So that's the trick. And so now that we have that trick in mind, we can talk about the running times and the algorithms for building or using a decision tree. So I'm going to talk about using it first. Suppose you've already built your decision tree and we want to classify a test point. The algorithm is very simple. You start at the root always, and you just walk down the tree. At each step, at each internal node, you make a choice, left or right, depending on the test point that you're trying to classify. When you reach a leaf, you return the label of that leaf. That's it. Simple algorithm. And so it's natural to ask now, what is the worst case running time? I'm assuming you only have to check one feature at each internal node. And so the running time is proportional to the depth of the tree in the worst case. I will note that if all of your features are binary and you have no other type of feature, then the depth of the tree cannot be greater than d. But quantitative features can go a lot deeper than that because one quantitative feature can split on it many times, not just once, as I walk down the tree. Now, for quantitative features, it's very common, but by no means guaranteed, that the depth of your tree will be around big O of log n. Could be a lot worse, but I don't think real-world data usually tests your tree that hard. So that's the classification algorithm after you've built the decision tree. What about the running time to build the decision tree to train it? So at each node, we need to implement the recursive algorithm I showed you. So if you have binary features, then at each node, you have to try splitting on each of those d features. And since there's only one way to split a binary feature, that means you're going to try d different splits. But for quantitative features, it's more expensive because for each feature you want to try, you're going to have to try big O of n prime d different splits, where n prime is the number of points in this particular tree node. But the interesting thing is, regardless of whether you are binary features and only have to try d splits, or you're doing quantitative features and you have to try nd splits, because this trick up here makes nd splits take only nd time, the running time for binary features and there's going to be, it's going to take order n prime d time to process a single node, not including the recursive calls that build the child nodes. Now, to analyze, we have to add this up over all the different nodes, not just one node. And for that, we're going to use an amortized analysis argument. What we're going to notice is that each point participates in a maximum of whatever the depth of the tree is, nodes. And within each node, we have just established that the amount of time that the algorithm has to spend looking at that node in any one tree node, looking at that point in any one tree node, is big O of d. So our amortized analysis argument is going to charge big O of d times depth running time to each training point. And therefore, the total time to build the whole tree is big O of the number of traits, n, times the number of features, times the depth. And I want to point out that since ND is just the size of the input, size of the design matrix, this is actually a very reasonable running time, especially since the depth is often log n. Final question about this? Yeah. Sorry, to choosing what data? Well, in terms of time to build the tree, actually, not really, no. Categorical data isn't much faster than quantitative data. And so that's kind of one of the points of this trick, is it's surprising that this trick makes quantitative data just as fast as categorical data, but it does. Yeah. Will this classify everything correctly? Well, you can certainly get 100% training accuracy by refining the tree until all the nodes are pure. Well, you may have to do it really deep, yeah. In the worst case, you might have each training point in its own leaf node. That doesn't usually happen, but it can happen. So yeah, the worst case is you refine all the way to one leaf node per training point. You have pure leaves. You have 100% training error. Unless you happen to have 2 points at exactly the same location with different classes, and then you can't have 100% training error. But barring that, you can get 100% training error, yeah. Other questions? Yeah. What do we consider the time for sorting the list? I mean, I think that linear time sorting algorithms like radix sort are totally practical and can and should be used for if your data set is large enough in the real world. So I consider sorting a linear time algorithm in practice as well as in theory. Does that answer your question? Okay. Yeah. Yeah. You can absolutely overfit data like crazy with this. You are absolutely right. But I'm going to answer your question next lecture, if that's okay, because that is a big part of the next lecture. It's what do we do about these trees overfit? And we will come back to it late in the semester, too, when we learn Ada Boost, which is a gloss on decision trees that also solves the overfitting problem. So there will be lots about that coming up. But all right, thank you very much. Have a good weekend.